All right, so I believe we are now recording. Welcome, Private Pilot Ground School. Today is Monday, April 20th. We're in the middle of a heated conversation of weather theory. It's exciting stuff, weather theory. I anticipate that we're going to be finishing weather theory, chapter 6, probably during today's class period. And that'll be moving us into weather products. Hooray for weather products as we continue forward, chapter 7. We'll have a test that'll be combined chapter 6 and 7 for weather theory and weather products. So that's kind of where we're at. We are recording. We've been uploading all these video streams to YouTube as well for your review. There's lots of homework assignments up. Just administrative, I've been getting some emails. The university is interested in who has missing assignments. So one of the things on my end is I've been working on some Excel sheets to send the university. So if you have missing assignments, now is the time to get them in. Missing assignments will affect your grade in this course. So before we get too deep into our presentation show, I just want to say good morning. Is there any thoughts, opening comments, questions, anything from the group? All right, Jacob Wheat has made it in. Awesome, great to see you. And we're still looking for Chance. We don't see Chance. All right, so awesome. Well, if nobody has any comments, then I can click the buttons to launch us into finishing up our conversation on weather theory. To finish up our conversation on weather theory, this will be chapter 6, section C. I'm going to click the button. We'll see if we can get the screen share working for us. Are you guys seeing a PowerPoint presentation about weather hazards, mature stage?
Yep.
Yes.
Sure.
Awesome. Good deal. We're doing the right things. All right, it looks like it's loading up. Weather hazards. So weather can be hazardous, especially for us flying in the atmosphere. So here's what the Prezi presentations look like. We've been cutting and pasting these into PowerPoint so they flow a little bit better with our streaming. Big vocabulary word here, thunderstorms. Single greatest threat to aircraft operations. Contains strong wind gusts, icing, hail, driving rain, lightnings, and tornadoes. Bad stuff. Ice in a beverage, good. Ice on an airplane, bad. All right, so this is one of the biggest test questions that you're going to hear again and again in the aviation world, becoming a pilot. In order for a thunderstorm to develop, 3 conditions must be met. The air must be unstable. There must be some form of lifting action, and we need to have high moisture content. So you're going to hear this question again and again on stage checks and check rides, on our chapter test, probably on the FAA written exam. What are the 3 ingredients to form a thunderstorm? We need to have unstable air, we need to have lifting action, and we need to have moisture. Typically, you'll find that the lifting action is going to be a front. So a lot of thunderstorms develop in frontal areas. Remember we talked about the cold front last time? But as we can tell throughout this presentation, there could be some other lifting forces as well. All right, I'm getting a notification. Chance is trying to get into our room. We'll let him in today. All right, so there it is. This is a very important question. You'll see this one again and again. 3 ingredients to form a thunderstorm: unstable air, a lifting force, and moisture. You got to have those 3 things to form a thunderstorm. All right, we got a few different types of thunderstorms. Severe thunderstorms, wind gust of 50 knots or more. It's pretty severe. Hail 3/4 of an inch or larger. That'd be a pretty severe thunderstorm. I agree. Now, the next vocabulary word in black says air mass thunderstorms. Scattered, usually driven by surface convection. So what's the difference? What is the difference? The difference is the lifting force. So if we have an air mass thunderstorm, that could be something that's, the lifting force could be more from thermals, convection. So we've talked a lot about how the sun puts off the shortwave solar radiation, heats up the earth, surface of the earth. So then like in the summer days, as the earth gives off its heat, pockets of rising air could create air mass thunderstorm. Not necessarily the same thing as a front. We're talking about heating of the air mass from below with the surface heating. So that'd be the air mass thunderstorm. It's not going to be as severe. You know, the cloud tops are not going to grow as high in such a situation. However, us as pilots are still, you know, should be staying 20 miles away from thunderstorms, according to the FAA. A lot of pilots will have personal minimums of double that, 40 miles. As we continue on, some different types of thunderstorms, we have single cell, supercell, multicell. They're helping us distinguish the differences. Single cell, they say it typically lasts less than 1 hour. So a thunderstorm is not a long-term event. That's really what we're picking up on. Single cell thunderstorm typically lasts less than 1 hour. Supercell, new vocabulary word. A supercell may last 2 hours. Supercell is going to be a very, very tall growing thunderstorm. In fact, supercell grows so tall it can penetrate the tropopause. So we said most of our weather is contained in the troposphere, that our tropopause acts as a cap on the atmosphere, that inversion layer that creates stability. Well, a supercell thunderstorm is so strong that it can grow higher and actually burst through the tropopause, and the tops of a supercell can actually go into the stratosphere. A supercell is really kind of what you're imagining with the Hollywood movies. So you imagine, you know, the large scale tornadoes, you know, really serious destructive weather, supercell thunderstorm. The next vocabulary word is a multicell thunderstorm. And we're saying that is a compact cluster of thunderstorms. For us, we normally think about squall lines, which is down there in green on the bottom of the slide. Squall line, generally associated with the most intense weather hazards for an aircraft. So as we try to prepare you for the FAA written exam and the test, squall line is a non-frontal narrow band of active thunderstorms. They say that it is non-frontal because those squall lines are actually 50 to 200 miles ahead of the cold front, ahead of the frontal zone. And a squall line would be a multi-cell thunderstorm where there are multiple cells. And as we continue learning throughout this presentation, that there's going to be different stages, different phases of the thunderstorm, and it can become the fact that one dying storm can be used to help feed the next growing storm. Thunderstorms. So here we're starting to see what's coming ahead. What's coming ahead, we're going to be talking about the thunderstorm life cycle. We can see that there's going to be 3 stages of a thunderstorm, 3 phases, starting with the cumulus, the next will be mature, and the final will be dissipating. So again, very common questions for your stage checks, check rides, and your chapter tests, FAA exams. What are the 3 phases of a thunderstorm? Cumulus, mature, dissipating, and then we'll have to be able to describe some characteristics of each. The first up to bat today, the cumulus stage. So we know that thunderstorms are an unstable phenomenon. We know that a thunderstorm is going to be more of a cumulus cloud, not necessarily a stratus cloud. Thunderstorms are more from cumulus clouds, and you can remember that because the thunderstorm comes from a cumulo or even cumulonimbus cloud, cumuliform clouds, that the thunderstorm first life cycle, the first stage, is the cumulus stage. So in green, it's telling us the lifting action gets things started for the cumulus stage. Could be because of a front, the cold front's causing some lifting action. Could be a warm front, but the warm front would be more stable lifting. Could be a occluded front. Gosh, that's a lot of lifting force. But it doesn't necessarily have to be a front. It could be convection, thermals, the hot summer day that's lifting air. It could be because of geography. So sometimes you have a mountainous area and rapidly rising terrain, and that could cause lifting force. Whatever the case may be, lifting force gets things started. The cumulus stage. As the air rises, it cools adiabatically. We know that the standard cooling rate is 2 degrees Celsius for every 1,000 feet that we climb. But wait a minute, this is unstable air. So it's going to cool extra fast. It's going to cool at a rate faster than 2 degrees Celsius. It's going to cool at a rate faster than 4.4 Fahrenheit. As the water vapor condenses, heat is released, and that feeds vertical growth. So I'm reading that middle black point there. As the water vapor condenses, heat is released, feeding vertical growth. So earlier, we had talked about latent heat energy transfer. And so we're speaking about how as the water vapor changes state of matter and becomes a liquid, which is a cloud, that the actual water molecule is going to release heat energy. And that released heat energy to the ambient environment causes more rapidly rising air. So it's a process through latent heat energy and adiabatic cooling that we continue to see this process grow taller and taller, higher and higher. We see the air lift, lift, lift. The water droplets are suspended, rising and falling in the updrafts. So that's the key word right there, friends, updrafts. When you think about the cumulus stage, and you're writing your notes on your paper right now, the cumulus stage is all about updrafts, rising air. Okay, Jacob Wheat is trying to get in. I thought we already had him in. Maybe he got kicked out.
No, sorry. I'm just switching over to my iPad. Sorry.
Oh, it's not a problem. I appreciate the feedback. I just have my grade book open for attendance, and so I wanted to make sure I got you marked correctly. Awesome. So water droplets suspended, rising and falling in the updrafts. Awesome. Hey, here's a fancy number for us. 20,000 feet. Cumulus stage, thunderstorm updrafts. It can grow up to 20,000 feet in as little as 15 minutes. So, you know, we're starting to see some warmer weather out there. Maybe next time you see a cloudy day and you see some thunderstorms rising in the area, sit out there on the back porch and watch some of these cumulus clouds rise. It's actually a pretty interesting event to watch this phenomenon in action. So cumulus stage, that is our first phase, our first stage of the life cycle thunderstorm process. Thunderstorm life cycle process, cumulus stage. Hey, look at that. We've made it to stage number 2 out of 3. Phases, stages of the thunderstorm life cycle. The next is called the mature stage. Mature, the water droplets, they grow too large. They can no longer be supported by the updraft, so they're going to start to begin to fall. What comes up must come down. This creates downdrafts. Look at that. It's bright green vocabulary. This creates downdrafts, and it signals the beginning of the mature stage. That is a test question right there. Be sure to document that piece of information for yourself. Downdrafts. So whenever us pilots talk about mature stage of thunderstorm, we talk about how there is updrafts and downdrafts. We talk about how we're starting to see the beginning of the first downdrafts, and what signals the downdrafts is the actual rain falling from the cloud. Precipitation. Updrafts and downdrafts exist side by side, creating nasty turbulence. Read that as wind shear. Wind shear. The leading edge of these downdrafts creates a gust front at the surface. So that means you could be several miles away from the thunderstorm, but as that thunderstorm pushes air out the bottom of the cumulonimbus cloud, it creates a gust of air, and you could be farther away from the thunderstorm and actually still experience the change of wind, and they call that gust front. With some weather systems, it can be so strong that they actually depict it on the surface analysis chart. If you all remember the prognostic charts we've studied before, you can actually see the line. It looks very similar to a trough type of line that they draw on the surface analysis chart, on the prognostic chart, and they label it gust front. So if you see gust front labeled on the chart, that means there's some severe convective weather nearby. Mature stage, that is the second stage of the life cycle of the thunderstorm process. We started with the cumulus stage. We've made it to mature stage. Mature stage, remember, updrafts and downdrafts. It is marked by rain falling from the cloud. Depending upon what textbook you read, some say when rain hits the surface, other textbooks say when rain falls from the cloud. Regardless, if we're starting to get actual precipitation, then there is rain falling and we are in the mature stage. The third stage and the final stage, dissipating stage. So the downdrafts are going to begin to spread out and they will overpower the updrafts. So upward movement is necessary for the release of latent heat. Without that vertical motion, the storm's going to begin to weaken. So what makes the storm grow? Updrafts. There has to be some lifting force to begin with, but once the updrafts gets established, then the updrafts continue to grow because of the process of latent heat energy transfer. At some point, it gets so cold that the water molecules condense and the liquid droplets will finally begin to fall. Once they start to fall, we now have up and down drafts. That was the mature stage. And once we get so much downdrafts become the overpowering dominant force, we've made it to the dissipating stage where we no longer have updrafts. Without the updrafts, the storm cannot continue growing. So dissipating stage is the final stage of the thunderstorm life cycle. So here we are, thunderstorm life cycle, and we got some nice pictures. Cumulus stage on the far left, we got a growing cloud, vertically developing cloud. Middle picture, we have mature stage. There are still updrafts, and the updrafts are going to start to have wind shear turbulence next to the downdrafts, all within the same proximity. The third and final stage is mostly downdrafts, and without the updrafts to feed the storm will be on the dissipating stage. We can kind of see on that far left picture how dark the bases of the clouds are. The reason the clouds are so dark is because the cloud top grows so tall. So as the cloud top grows so tall, it casts a shadow on itself. So this is a question you'll hear again and again. The 3 ingredients to create a thunderstorm, and then the 3 phases of the thunderstorm. Typically, the next conversation would involve microburst. So just kind of thinking about this last stage, which would be dissipating stage, all downdrafts, we get a new vocabulary word. I think that we're going to see it again later in the slide, but right here is really relevant, and that's the word microburst. Microburst. We actually watched a video about this when we were all together early in the semester. And a microburst is an area of severe downdrafts. How severe? Up to 6,000 feet per minute. So microburst, area of intense downdrafts, up to 6,000 feet per minute. You will hear that information again on the test. Why do they call it microburst, M-I-C-R-O? Because it is very short duration of time. So seldom does a microburst last longer than 15 minutes. So these are all questions you'll hear again and again for stage check, check ride, and tests. Microbursts, seldom longer than 15 minutes. Basically, it's a downburst of air, cold column downburst of air, which is very similar to what we're talking about with dissipating stage. Your examiner might ask you, he might say, hey, how do you avoid microburst? How do you avoid microburst? And the answer is to avoid thunderstorms, to avoid areas of convective activity. The idea is that microbursts are associated with thunderstorms. They are associated with convective activity. Okay, we're moving into thunderstorm hazards. Turbulence. Better tighten your seatbelts, folks. Turbulence. Turbulence, air moving in opposite directions in very close proximity creates violent turbulence. Maybe we should have some participation. Any class participation? What should you do if you get caught in some turbulence?
Slow down the plane to maneuvering speed or less than.
100% correct answer. Very, very nice. So if you encounter turbulence, you should slow the airplane down at or below maneuver speed. If we are, yep.
First step would be to not panic. Just trying to say the obvious because, you know, some people would probably panic and then get into a bigger situation than what it could be.
Very good thinking from Nick. Awesome. Yeah, don't panic, keep calm, fly on, slow her down at or below maneuver speed. Remember, if we are slower than maneuver speed, the worst thing that can happen is stall. If we are at or below maneuver speed, the worst thing that can happen to us is stall. If we are faster than maneuver speed, we could cause structural damage, structural failure. We would much rather have to recover from a stall than to try to figure out how to fly with a broken wing. So turbulence. You'll have another test question about this topic. It'll say, if you as a pilot get caught in turbulence, what should you do? The correct answer is to maintain attitude, A-T-T-I-T-U-D-E, maintain level attitude. You as the pilot should accept the fact that you will have changes in altitude, A-L-T-I-T-U-D-E. So you as the pilot, if you get caught in turbulence, you should maintain level attitude and accept the fact that there will be changes in altitude. You accept the fact that there will be changes in airspeed. You're going to get rock and rolled, knocked around, but your job is to keep the blue side up and the brown side down. Turbulence. The bottom of our slide says that another turbulent area exists near the surface in front of the thunderstorm in the shear zone. So we've talked about wind shear. Wind shear would be very similar to the idea of turbulence, where you have two different airflows that are opposing each other in a very close proximity. Turbulence, wind shear. Another vocabulary word you typically hear about is low level wind shear, LLWS, low level wind shear. Can be very dangerous because low level means we're trying to take off or land. We are close to the ground, low level wind shear. So if you're in an area where there's low level wind shear, it's probably not a good idea to try to take off or land at that airport. If you have the fuel, you should fly to a different airport where there's not as severe low level wind shear. Up at the higher altitudes, it's common to have wind shear. Think about the jet stream. Whenever an airplane gets near the jet stream, there's going to be wind shear, a turbulence area as that aircraft gets near the jet stream. At that case, the airplane has so much altitude, it's probably not at risk of colliding with the ground. So that's why they distinguish the difference between the low level wind shear and the upper air wind shears. Turbulence. All right, so we are discussing hazards of a thunderstorm. These are hazards of thunderstorm. We just did turbulence. Now we're into lightning. What is lightning? Well, it's caused by the release of latent energy and static discharges on a massive scale. Rarely causes injury or substantial damage, could cause a temporary loss of vision, punctures to the aircraft skin, damage to avionics. Lightning. Everybody's done it before where they get shocked, static electricity. Maybe you're walking with your socks on the carpet rug and you touch the metal door handle and shocking. That's exactly what's going on. So we have turbulence, we have wind shear, we have up and down drafts. There's so much friction. Read this as friction. So there's so much friction in the atmosphere as all these strong wind gusts barrel by each other, and we build up static electricity. That static electricity grows so large, so strong, that a thunderbolt, a lightning bolt, will shoot out of that cloud. That cloud has become charged with all sorts of particles. There are different types of lightning. When we start to study all the different METAR codes, you'll see many different types of lightning. So the idea is that you could have lightning that's cloud to cloud, where one cloud shoots a lightning bolt to the next cloud. You could have lightning that's cloud to ground, cloud to ground. That's more what we typically think about when we imagine lightning. The cloud has become so charged that the lightning bolt connects down to the ground or the planet Earth. Lightning. I had a friend that got struck by lightning in his aircraft, and it actually created a very large hole in the back tail section of his aircraft. So he said he was flying along, and he said the words, "Man, I never thought that I would, he never got so close. He got too close, and he heard a big lightning bolt, and he jumped out of his seat, and he said, wow, that was really close. It was so close, it actually had hit his aircraft. It was a TBM. And the lightning bolt exited the tail end of the aircraft and left a very large hole. There's a lot of stories of pilots and lightning. A lot of different stories of it on the internet, and when you talk to pilots that have flown a long time, bad stuff. We on our aircraft, well, number one, we're not going to go flying near any thunderstorms or lightning or convective activity. We're going to maintain at least 20 miles from any thunderstorm. In fact, we're taking personal notes more of 40 miles. But this whole static electricity buildup conversation is relevant to our airplane. Our aircraft is a very slick aircraft with the Cirrus SR20 and the carbon fiber design. When you get faster airplanes that are slick, aerodynamic, we can actually have static electricity build up on our aircraft. And so you notice when you pre-flight the airplane, we have static wicks. We have small wicks that protrude off the trailing edges of our airfoils. Those static wicks help dissipate the static electricity charge that could build up on our airplane. Without those static wicks, we could actually hold the static charge on our aircraft. So if you fly an older style airplane that doesn't have static wicks, and you start to build up static electricity on your aircraft, you might notice it as the pilot because your radios get extra staticky and it's hard to hear and transmit. A lot of the stories go that when that airplane lands and the wheels touch the ground, the radios become more clear because that electrical charge was able to dissipate and ground itself out on planet Earth, the ground. There are other stories of St. Elmo's fire. St. Elmo's fire. Very interesting stuff. Some of the older style airplanes, like big fast jet airliners, they would be flying through the atmosphere, and they would build up so much static electricity on their ship that they would literally see the static charged ion particles on their windscreen, and their windscreen would start to flash and jump around in front of them until it became so strong that the lightning bolt would literally shoot off the nose of their airplane. They would call this phenomenon St. Elmo's fire. Very interesting stuff. So it all boils back to the same thing, and that is friction. Friction, as air molecules or as molecules in general rub together, rub up against each other, rub beside each other, there's going to start to build up some static electricity. When it happens in the atmosphere and the clouds, we usually call it lightning, when that violent static electricity discharge is finally released. It actually comes from ground to cloud, although many people talk about, it looks like it's going from cloud to ground, but the speed of light's pretty fast. Lightning, that is a serious hazard of thunderstorms for us as pilots. Ah, well, hail. So hail, that's a pretty nasty looking picture down there in the front. That pilot got way too close to some bad weather. Hail can occur at any altitude within or outside of a thunderstorm. Hail can be thrown several miles from the storm. Hail can cause immense damage to the aircraft. Bad stuff, hail. So this is one of the big reasons why we're supposed to stay 20 miles, if not 40 miles away from thunderstorms. We're moving at 100 miles an hour. We don't want a big hail ball coming and hitting us, cracking our windscreen open. Gosh, imagine, it's not good for the engine, especially a jet engine, to try to ingest the hail either. So hail, there are updrafts and downdrafts, and that hailstone keeps rising and sinking through the draft process of the thunderstorm until finally it grows so large and so heavy that it gets thrown and ejected and cannot remain suspended in the convective currents any longer. All right, hail. Tornadoes. I think we all know why these are so dangerous. So it's really just the fact of wind shear, gosh, very, very strong winds, tornadoes. That would be a supercell type of event, and we don't want to be flying anywhere near that level of convective activity. Weather hazards. Okay, we're talking now about low-level turbulence. It's defined as turbulence that is below 15,000 feet, usually occurs due to convection or surface friction. Low-level turbulence. This is predominantly what we're going to see in our airplanes. Mechanical turbulence. Obstacles, maybe rough terrain, interfere with the wind flow. The stronger the wind, the higher the mechanical turbulence will spread. So this is the story of my old airport. At my old airport, we had a setup very similar to this picture, the top picture there in the center. And there were airplane hangars right next to the runway. There are many airports you will fly to, and if the wind is coming from the left to the right, and there is some sort of obstacle to the left that would interfere with the wind pattern, well, that means you're going to have changing winds. You're going to have uneven winds. You're going to experience turbulence right there during the moment of your landing. So that mechanical turbulence can cause a lot of issues when you're at slow airspeeds trying to land. In the very bottom picture, we can see it more on a larger scale, such as a mountainous area. And we're going to see a lot of turbulence, mechanical turbulence on the backside of that mountain. So this is the reason why if it's very strong windy days, you as a pilot might want to add extra airspeed. If you come into land with extra airspeed, then you might have extra control. Your flight controls can be more effective if you have more airspeed. But like everything else, it's a balancing game in life, because if you come in too fast, then you're not going to land. If you come in too slow, you're not going to have the good control to try to fight this situation. You, as a student pilot, if you ever have any doubt, go around. Go find another airport to land at. Risk management. And in the mountainous area, we talked about that if you are, let's say 2,000 feet. In mountainous area, you should stay at least 2,000 feet above peaks. So that way, if there is any mechanical turbulence associated with that area, you have a bigger buffer zone between you and the danger. So mechanical turbulence. You can even experience this when you're out pre-flight in the airplane. You can see how there are rows of hangars, and when you step between the different rows, you can feel the difference in wind, as some areas are more sheltered and the wind can rush around other areas that are more open. So just remember that whenever you're looking at your landing locations. Convective turbulence. Okay, so this is what we've been speaking about a lot lately. When we talked about the air mass thunderstorms, convective turbulence. When we talk about thermals, convective turbulence. The air is heated by contact with the warm surface below. That warm surface below, the land mass, is going to create rising columns of air. We call those thermals. Typically, you will find that there is a capping layer in the atmosphere that will improve your ride. So maybe it's bumpy at lower altitudes. Maybe you've experienced that when you fly around with your flight instructor, that when you're within 3,000 feet of the ground, it's bumpy. But if you climb to extra high altitudes, maybe 5,000 or 6,000, you might find smoother air. And that's because there reaches a capping layer where the air is able to equalize, where the hot and cold, the rising and sinking airs are able to achieve equilibrium. There's probably going to be a temperature inversion around that altitude as well. So what lessons does this mean for you? If it's a hot summer day, as we're moving into the summer season, you can expect on a hot summer day to find some bumpy, turbulent air at lower altitudes. If it's a day to fly across country, you might want to plan for an extra high altitude. I don't say anything extreme, but if you get above 5,000, maybe at least above 3,000, 6,000, 7,000, these are some good altitudes where you might find smoother air. It's very common that if I'm flying across country, I might talk to air traffic control and tell them that I'd like to try 2,000 feet higher. I'd like to try the next appropriate VFR cruising altitude above, so that way I could possibly find smoother air. Turbulence. We are still talking about turbulence. Now this turbulence is more because of the frontal zone. Remember the cold front, warm front, occluded front, stationary front. Frontal turbulence. Frontal turbulence occurs in a narrow zone just ahead of the fast-moving cold fronts. Any front moving faster than 30 knots will produce moderate turbulence. So that's a pretty good speed. 30 knots may not seem that fast, but if the whole air mass is moving at 30 knots, that's very significant. All fronts moving over rough terrain produce moderate or greater turbulence. Wake turbulence. Well, this is a type of turbulence, yes. Maybe not so much weather, but it is turbulence, and it's a very good topic for us to keep fresh in our brains. You'll have multiple questions about wake turbulence on that FAA written exam. So we discussed, remember from our aerodynamics chapter, that wingtip vortices persist long after the aircraft generating them has gone. Wake turbulence is most severe when the generating aircraft is heavy, slow, and clean. So wake turbulence, wingtip vortices, these are elements of induced drag. This is the turbulent air that is left behind after a very large aircraft flies in that area. It is going to be the strongest when that aircraft creates the most amount of lift. So you think about that as maybe a takeoff when the aircraft is slow, at a high angle of attack, at a high power setting. You, as a small Cirrus pilot, are going to want to avoid flying through a 747's wake turbulence. So you need to try to stay above the wake turbulence path. Wake turbulence, wingtip vortices, they sink. They sink and they flow with the wind. So you, as a small Cirrus pilot, would want to try to stay above the larger airplane's flight path. You would try to stay upwind of the larger airplane's flight path. If you need to take off right after a 747 has taken off, the first step is to wait. The FAA recommends a minimum of 2 minutes for the wingtip vortice wake turbulence to dissipate. So that's a common question for check ride. Examiner says, hey, Cirrus 4-1 Victor uniform, you're clear for immediate takeoff following the 747. What do you say? Your answer is negative, I will wait. You will wait at least 2 minutes, FAA recommended. And then even after the 2 minutes, you would want to be conscious, aware of what point did that larger aircraft rotate. Where the larger aircraft rotates and their wheels come off the ground and that airplane begins creating lift, that is the point where they're going to develop the wake turbulence wingtip vortices. We are a smaller aircraft, so we want to rotate and lift into the air at a point before the larger airplane rotated and lifted. We're not going to be able to outclimb that 747. So for us, we would want to sidestep upwind because the wingtip vortices will flow downwind. Wake turbulence. Let's talk about landing. Let's say there's a large 747 that lands in front of us. During our final approach path, we want to stay above the flight path from the larger aircraft. We want to touch down at a point after the 747's touchdown point. The whole time we need to stay above the path where the wingtip vortices wake turbulence exists. Wingtip vortices and wake turbulence is invisible, so we need to take extra precautions to avoid them. Wake turbulence. CAT, clear air turbulence. Invisible trouble. Clear air turbulence occurs in the space between a fast and slow jet streams. It cannot be seen. Aircraft radar cannot detect it. Main cause, planes flying at higher altitudes, moves through the air, different air densities, different temperatures. Clear air turbulence. Slow jet stream, different currents conflict with the jet stream. Fast jet stream, currents shift, disturbing nearby air. So the whole idea here is that we have this phenomena in the atmosphere called the jet stream. We know that the jet stream exists at the place where troposphere meets stratosphere. That is commonly called the tropopause. The tropopause is where the jet stream lives, and it is a column, a very upper air phenomenon, somewhere between 20 and 37,000 feet, depending on the day, probably somewhere near 36, 37,000 feet for our mid-latitudes. And there are two different jet streams in America. We have the northern jet stream we'd call the polar jet stream. We have the southern jet stream we call the tropical jet stream. We can study upper air charts to actually view the jet stream. And the jet stream typically makes some bends. It doesn't just flow straight west to east. It'll normally have some bends and some snake S shapes in that jet stream. Think about it this way, folks. Wherever the jet stream takes tighter, sharper turns, that's where you're going to find more turbulence. I've actually heard pilots call them flight attendant killers. There's a lot of stories where bigger airliners are flying along, and if they hit some very strong turbulence, anybody that's not strapped into the seat can literally be ejected and hit their head on the ceiling. So it's very serious stuff. You know, the captain of the airliner turns on the fasten seatbelt sign for a reason. And if you're in an aircraft that's flying at those higher altitudes, it is a very serious phenomenon, a very serious type of turbulence that you need to watch out for. They call that CAT, C-A-T, clear air turbulence. And it's in the transition zone where you have the very fast moving center of the core of the jet stream in the transition zone as you move away from that very fast core of the jet stream. More turbulence. Wow, turbulence. Mountain wave turbulence this time. Mountain waves. Mountain wave turbulence. Possible it occurs when the wind across a mountain ridge is 40 knots or greater. These wave patterns can extend 100 miles or more downwind. So in this case, we have the upwind side of the mountain to the left, the downwind side of the mountain to the right. And if we have stronger winds, our slide is telling us over 40 knots, yeah, you're going to see some very strong turbulence occur because of this phenomenon. Remember mechanical turbulence that we talked about in a few slides ago? So as the air rushes over the mountain, we create these spiraling, snaking types of wind currents in the atmosphere. What you're seeing is a formation of interesting clouds. We are seeing some very interesting clouds that are showcasing the turbulence. So most turbulence is invisible. Most turbulence is invisible. But in this case, we're starting to see a very fancy type of cloud called a lenticular cloud. So you can see it there. We have primary wave, secondary wave, and then third wave. And each time you're seeing a very funny shaped cloud. The FAA written exam will call it an almond-shaped cloud. An almond-shaped cloud. So if I use my mouse, I can try to show you. This cloud right here is what they're talking about. They call it an almond-shaped cloud. I think it kind of looks like a lens. I think it kind of looks like a lens. And I think about the word lens and the word lenticular cloud. But this is a turbulence cloud. It has very sharp, defined edges. Like this is a very sharp, defined shape. In general, the more sharply defined shape, usually the more faster the air is moving in and around that cloud. So as the air comes from upwind to downwind, we're seeing areas of up and down drafts. It's almost like a rotary action. So here's some turbulent rotors at the lower altitudes. These turbulent rotors are areas of turbulence. And you can see the mark to the shapes as we get these almond lenticular clouds. If you were a glider pilot and you did not have an engine and you were looking for lift, it's showing you that you can find lift on the upwind side of the rotors, where there is sink on the downwind side of the rotors. For us as a powered aircraft, it's still valuable information because if you get caught in an area of sinking air, you might be able to realize that there is an area of rising air somewhere nearby. The big lessons we're getting here: mountain wave turbulence, lenticular clouds. You'll see this question on the FAA written exam. Lenticular clouds are almond shaped and they indicate very strong turbulence. Weather hazards. Wind shear. Okay, so what is wind shear? A sudden, drastic shift in wind, speed, and/or direction. Can occur at any altitude, could act horizontally or vertically, could cause dramatic loss of lift, violent changes in vertical speed and altitudes. Wind shear. So I think our first line was what you'll see on the FAA written exam. What is wind shear? A drastic shift in speed and or direction. When you take the FAA written exam, they actually use the word velocity. So what you're learning is that the word velocity is a double fold. The word velocity stands for two different facts, two different pieces of information go into the one vocabulary word, velocity. When you say velocity, you imply speed and direction. When you talk about velocity, you imply both speed and direction. So we could be talking about wind speed, we could be talking about wind direction, we could talk about wind velocity. When we talk about wind velocity, we account for both speed and direction. So that's the word I believe you see on the FAA written exam. But wind shear could be any of them. Doesn't have to be both. Remember the clear air turbulence? So drastic shift in wind speed or direction. So you could just say drastic change in wind velocity in a small amount of space. Oh, icing. My old flight instructor just told me again and again, ice in a beverage is good, ice on your airplane is bad. And now there's a whole lot of possible ice to talk about. So we'll probably talk about some icing and then we'll take our break. Nobody has to, because everyone will have to have human needs. But we're going to think about some icing first. Let's try to get through some icing. So icing, it can accumulate when visible moisture is present and the aircraft surface temperatures are at or below freezing. That is very important information. So if you're writing down in your notes, taking notes, icing accumulates, you'll have this question. It'll say, what are the requirements for structural icing to form? Your examiner will ask you on the day of your test, how do you know if structural icing is going to be an issue on today's flight? And there are two requirements for structural icing. We need to have one, visible moisture. We need to two, have a collecting surface that is at or below freezing. And that's what it's telling us here. We need visible moisture and we need to have an aircraft surface temperatures that are at or below freezing. In this slide, they're telling us about two different types of structural icing. They're telling us about rime ice, R-I-M-E, rime ice. Supercooled water droplets freeze immediately upon impact. They're telling us about clear ice, larger droplets that freeze more slowly. Rime ice is way more common. Clear ice is not as common, but clear ice is more severe. Why is clear ice more severe? It's more dense, which means it's more heavy. Clear ice, it runs back. So rime ice might predominantly form in the leading edge area. Clear ice can run back. They can call it run back ice, and that clear ice can cover a larger surface area of your wing. That clear ice is going to run back farther. So if you was an airplane that had anti-ice equipment, de-ice equipment, if you had fancy boots on the front of your wing, if you had a hot wing, if you had an aircraft with fancy glycol ice melting fluid that spits out the leading edge of your wing, that clear ice could still be extra hazardous to you because the clear ice runs back beyond the ice protection equipment. So even if you do have an airplane that's certified to fly in known icing conditions, you should not fly that airplane in known icing conditions if you can help it. That equipment is designed really just to help pilots get out of an icing situation. It's not a free ticket for you just to go fly your airplane into icing conditions to begin with. Icing. Typically, we say that there are three, maybe four, let's say four today. There are four types of structural icing. There are actually four types of structural icing: rime ice, clear ice, mixed, M-I-X-E-D, mixed ice, and then frost. So we've talked about rime, we've talked about clear. Mixed ice could be somewhere in the middle. It could have both some rime elements to it and some clear elements to it. Frost. Frost is a special type of structural icing because we do not pick up frost while we are flying. Frost would be accumulated on the ground, and you should notice frost during your pre-flight procedure. If your aircraft has frost, then you need to remove that frost before flight. A few more notes for icing, and then we'll take our break. Many times for icing, we as pilots need to think about structural ice. We need to think about the temperature ranges of structural ice. So I will teach you that you can have structural ice in a temperature range of +5 Celsius down to -20 Celsius. So if you're taking your notes, please take notes. Make sure to write this down. Structural ice temperature ranges. I'm teaching you +5 down to -20. There are some instructors that might be extra conservative. They might teach +10 down to -25. If you study the FAA literature, they have an advisory circular, AC advisory circular on this topic. They might actually say +5 Celsius down to -15 Celsius. What you're learning is that there's a certain range, a certain temperature range where we can expect structural icing. That area of +5 to -5, the warmer side of the spectrum, that's where you're more likely going to see the clear ice. And then the colder temperatures is probably more where you'll see the rime ice. The clear ice accumulates extra fast. Ice. So as we continue forward, it's going to get into some visibility, restrictions visibility. We're about to take our break. I'm going to hit the button that stops our screen share. If anybody has any general questions for the class, I'm more than happy to address them now.
Did you say that clear ice happens a lot faster than rime ice?
Affirmative. Really think yeah, that's the answer. Clear ice builds up way quicker than rime ice. Think like freezing rain. It just happens so quick.
And at what temperature you said that happens at? You said that it's more possible at -12 Celsius or +5?
I'm saying that clear ice is the warmer side of the spectrum. So I think I gave you a temperature range of +5 down to -20. So if that's my temperature range that I'm working with, I would say like +5 to -5 would be more of the clear ice, and then everything colder would be more rime ice. But again, there's a lot of variables, but those are just, something to work off of.
Copy. Thank you, sir.
Great questions. We love the participation. We love the interaction. Now's a great time for questions if there's any going around the room. All right, well, we're going to take a 10-minute break for some human needs. We're going to be back in 10 minutes, and we're going to continue on with our weather theory, and then we'll be getting into weather products.
Copy. Thank you, sir.
Thank you.
Can everybody hear me all right?
Yeah.
Yep.
Yes.
Yes, sir.
Awesome. I'm getting some good feedback. Good stuff. So we're getting close to finishing chapter 6. We're going to finish chapter 6, weather theory. We'll move into chapter 7, weather products. We'll have a combined test that's both chapter 6 and 7 together. And from there, we're just getting ready for the final. So administrative wise, today is April 20th. So we have this week, we have next week, the week of the 27th. That takes us into May 4th. That's really our last week of class, because the week of May 11th, that is now finals week. So I'm not going to be trying to introduce any new material on finals week. On finals week, they'll just be tests. How are tests going to work this semester? I've been talking with the department, with my boss, and how it's going to work is that I'm going to create 4 tests, and they will all be basically like FAA written exams through Blackboard. They're timed. It's the exact time limit of a FAA test, and there'll be 4. So you'll be able to take, I'm thinking it'll probably, I'm trying to debate, and I'm open to suggestions. If I should just make them all available at once, or if maybe I should, have one of them available Monday and then Tuesday and then Wednesday. But the idea is that I have to see at least 3 test scores where you score above 80%. I'm going to offer 4 tests. Whichever test score is your lowest, I drop that grade. Is this making sense?
Yes, sir.
Yes.
Yeah, it does.
So that's how we're going to do it. This is what I've been talking with Sean and Jason, and the way we're going to do it is on actual finals week, there's going to be 4 different tests for private pilot ground school. You have to take at least 3 of them, and you need to score above 80%. There'll be 4 available, so if on one of those first 3 you don't score above an 80%, you have the option to take the 4th test, and you need to have at least 3 of them that are above 80%. If you do not have at least 3 test scores above 80%, then you fail the class. Right now, this class had been set up so that way that final exam is worth 50% of your grade. Nowadays, with our distance education format, it's problematic. It's problematic because I've been noticing a lot of suspicious activity surrounding testing. Some things that Sean told me about, he's our assistant chief flight instructor, is that our Blackboard can monitor you while you're taking the test. So if you have multiple tabs open and you start clicking through other tabs, he's saying that for more than 2 minutes, that if it shows you as clicking around through other tabs and other websites more than 2 minutes, that Blackboard records that information. But regardless, it's still not the perfect secure testing environment that we normally would have for our course. So I have been discussing with the boss. The boss has been talking to me about possibly changing the weights of the grades. So traditionally, this class had been set up so that way 50% of your classroom grade was dictated on that final exam. But with this whole distance education format and us not able to verify if anybody's trying to be unethical or cheat on their tests, the boss has been talking with me about changing the grade weights for the class. What would that mean? It would mean that maybe the final, instead of being worth 50% of your grade, might actually only be worth 25% of your grade, or a different percentage, just less than 50. What would that mean? It would mean that your homework assignments would actually be worth more points. So I've only had, one conversation with Sean and Jason, our chief flight instructor and assistant chief flight instructor, and this is some of the information that they're talking about implementing in their classes, and they're encouraging me. So as we move forward, I'm just keeping everybody up to date on what's going on with grades and progress. I opened up the class and I explained to you that I'm getting, emails from the university about students with missing grades. So the university is now logging into our Blackboard site and paying closer attention to our Blackboard. And so they notice that there's some students that have a lot of missing assignments. So if you're one of those folks that has missing assignments, the homeworks are going to end up being probably worth more for your final grade than before with our new distance education format. So if you still have missing assignments, we need to get those in. We're about to have a test. Once we finish chapter 7, we're about to finish chapter 6, probably today, and then we're moving to chapter 7. Once we finish chapter 7, there'll be a test for chapter 6 and 7 together. I will not be giving a test over chapter 8, 9, 10. We will review some of the information from chapter 8, 9, and 10 together. We'll review it together, but I won't have a separate test for those chapters. Those chapters will just be into the final. A lot of them are math problems where we, do math. We build upon all the knowledge we've learned all semester to apply for flight planning. And then the actual finals week is May 11th. And during finals week, there will be 4 tests through Blackboard. And of those 4, I drop your lowest test grade. So I think I said it all a few times. Is there any thoughts or questions about what's going on as we move forward?
So you mentioned that we weren't gonna be tested on 8 and so forth and so forth. Now, that being said, could we work ahead and work on the key terms and turn all those in from the remaining chapters and get credit for those, or are we just gonna specifically stop at a certain chapter?
Extra credit. So we're in chapter 6. We're about to do chapter 7. So I'm expecting to have normal assignments for chapter 6 and 7. Your vocabulary, your short answer, your homeworks for each section for 6 and 7. When you talk about like 8, 9, 10, that's all extra credit. So if you're doing vocabularies, if you're doing homework assignments, if you're doing anything else in Blackboard for chapter 8, 9, 10, that's all just extra credit. I'll give you extra credit in the grade book for it. Go for it. But it's not required. That information will end up coming through on the final. If that answers what you're asking.
Yes, sir, it does. Thank you.
All right, so it's an open floor. If anybody else has more questions or thoughts, I think I covered that a few different times. And what I'm noticing in the grade book is that I'm really lacking quiz grades. I haven't been able to give you guys quizzes per se. So I'd like to try to do a quiz today. Everybody's logged in, and so it should be really easy. We're going to try to use the Zoom Messenger app. So I think you can just click on my name and send me a private message. And I'm going to put a few questions up on the screen, and this will be your chance to submit to me your responses. And that way I can gather some more grades for the grade book for quizzes. you know, I would hate to think that there's anybody out there that just kind of like logs in for attendance and then, you know, doesn't pay attention to the video. But I guess if nobody responds to the quiz, then maybe I know that's what's going on. But I'm gonna put up some questions at this time, and you're gonna try to submit them through like the private chat feature of the Zoom app. And we're gonna see if we can gather some quiz grades. If it falls apart, so be it. We'll see if we can make it work here for day for us. So at this point, I'm gonna hit screen share.
Quick question.
Yeah.
Would it be okay to send you in an email if we can't figure out the instant messenger?
Yeah. I'm not against that. I'm not against that one bit. It could be problematic though, because some people might possibly have issues. Like if you're on a smartphone or if you're on a tablet, and for you to have to change apps to try to email, that could create an issue for some people. So that's why I thought the Zoom chat might be better. But yeah, if you're on a computer and you can just bounce between different tabs and you can fire an email off, doesn't matter to me. I'm just trying to collect some more grades to help, you know, keep padding the grade book up and give everybody a chance to score points. Great questions. Okay, so I believe you all see my PowerPoint slides, and we'll have a few questions here. We'll have question number 1, and it'll be describe the rotation of low pressure system. And I'm going to give you guys 1 minute to shoot me a response. It should be very, very simple. So you got 1 minute for this question. All right, so we're going to move on to question number 2. Question number 2 today.
Heads up.
Yeah.
I would probably tell, what's his name? Someone sent it to everyone accidentally.
Nope.
I figured it out. Next one won't be like that.
Hey, we're trying. We're trying. We really are. Awesome. Cool. Hey, you know, if somebody gets a free point, so be it. You know, we're going to keep trying to move forward. Good thinking. Thank you. Question 2. We're going to say a land mass and then you have the option of absorbs. We'll just say absorbs. A land mass absorbs heat, and then you could say blank rapidly than a water mass. And basically, you're either going to use the word more or less. Give you a 50-50 chance of that one. So you got a minute for that one. All right, so there's a minute here. This one's going to be a little more tricky, but I'm trying to prepare you. So we'll see where we're at on this one. 3. What height AGL do you expect cloud base if surface temp 65 Fahrenheit and dew point is 56 Fahrenheit? And I'm gonna give you a hint. Use lapse rate of 4.4 Fahrenheit per 1,000 feet.
I actually have a question about this after we're done with the quiz.
Perfect. Thank you for chiming in. Let's see if we can where everybody's at. Let's see if everybody's at on that question there. Just try to give it your best. I'm gonna give you a minute on the clock here. Just a few quick seconds as somebody might finish their math problem here. Maybe 10 more seconds here. All right, we'll get a few more points while we're here. New question. Question 4. Oh. What ingredients do you need? Let's make it more simple. What are the ingredients to form a thunderstorm? All right, so I'm going to give you a minute for that one. All right, and one more final question for you, and this will be it. What are the stages of a thunderstorm? All right, so I'm going to put 1 minute on the clock. All right, so there's 1 minute on the clock. I'm logging into my email. If you are going to try to send it as an email, I ask you to send it now. So if you are going to send it as an email, please send that now. If you're going to use the Zoom chat, go ahead and type the Zoom chat. Oh, let me turn off the screen share. Okay. So I got a lot of information here from everybody. Let me copy this so I don't lose it all. Oh, wow. A lot of information. Okay. Copy. Awesome. And let me paste that into a document so I don't lose it. So what do you guys think? Good, bad, ugly?
Good.
Yeah, I think it went good.
Yeah, I like it.
Wasn't anything too tricky. Did I ask anything super tricky? Oh, one new message. Somebody else is trying to get their answer in.
Yeah, that was me. I guess it didn't go through, or I accidentally like deleted it. I went back and looked at your question and it deleted it. It's kind of weird to use off the phone. If you type a message on your phone and then you go back to the question to look at it again to make sure it deletes it. So I guess I didn't hit send.
Hey, we're all learning. We're all flexible here. So I just posted all those onto a document. Let me go back and grab Kai's because he sent one more after the fact. Yep, I agree, Kai. Good job. Okay. All right. So at this point, everybody should have their answers in. And do you guys want to review over that real quick?
Sure.
Yeah, that sounds good to me.
All right. So quick review. We just had these questions asked to the class. If you, I see what the current timestamp is. So if you're trying to email answers in, hopefully they got emailed in before now. Question 1, describe the rotation of a low pressure system. That should be counterclockwise. That's the answer we're looking for, counterclockwise. Remember, the L's of a low pressure system, it's left-hand turning, it's lifting force, it's less stable. So left-hand turning is counterclockwise. So if you have something about counterclockwise, lifting, left-hand turning, something of that nature, you'll probably get the points. Number 2, a landmass absorbs heat blank rapidly than a water mass. The landmass will absorb heat more rapidly than the landmass. So the landmass will heat up more rapidly than water. The landmass will release more rapidly than water. So we're trying to learn about the difference between water masses and land masses. Land masses absorb heat quicker and release heat quicker. The water mass holds onto its heat longer and takes a longer amount of time to heat up. That's number 2. Number 3, this is the tricky one that Isaac was asking about. At what height AGL do you expect cloud base if the surface temperature is 65 Fahrenheit and the dew point is 56 Fahrenheit? So up here, I'll do the math for you real quick. And we have 65 subtract 56. So what are we at? 6? No, we're at 9. That's 9 degrees difference. So we have a 9-degree temperature dew point spread. That's the temperature dew point spread. Okay, so we're going to take 9 division sign by 4.4. And we said that equals 2 point something. 2.04. So roughly, 2,000 feet AGL is the base of the clouds. So I remember Isaac said he had a question about that one. I don't know if this helps or not.
Well, when I was going through Sporty Study Buddy, I asked one of the same questions, but every time I gave an answer, it was like it was always 1,000 foot more. So anytime I go back in and retake the test, I would just automatically add 1,000 foot to whatever the answer was, and I'd get it right. I don't know why it was doing it like that, or.
I have a guess. You would have to actually find the real question so we can analyze the real question that's troubling you. But I have a guess. My guess is the words AGL versus the words MSL, above ground level versus mean sea level. So in my question today, it says what height AGL, above ground level. But if there are other questions on the written exam that might ask MSL, mean sea level. And so if the question was asking about mean sea level, then you might have to do an extra step of math with field elevation.
Okay.
And so I'm guessing that maybe the field elevation in your example problem maybe was 1,000 feet field elevation, and you had to either add or subtract to compensate for that 1,000 foot field elevation to begin with, maybe.
Quick question. If you guys are done, I don't mean to interrupt.
No, he answered it. You're good, man.
Isn't that very similar to the question that's in the back of the chapter 6 question?
I literally gave you the exact same question. I'm not trying to pull any tricks on you. I'm trying to help you out. Yeah.
It just looked familiar, and I was just double checking.
Yep, good. So I'm not being that tricky with you. I'm asking a lot of questions that hopefully if you're doing homeworks and reading the questions in the back, you should be prepared for this. Good job.
Thank you. Bye.
Yep. So I think we're moving on to number 4. What are the ingredients to form a thunderstorm? We literally just covered that one in the first half of class. Unstable air, a lifting force, moisture. That's it. Those 3 things. You need unstable air, moisture, lifting force. So that's what you're looking for number 4, those 3 ingredients. And then number 5, what are the stages of a thunderstorm? We literally covered that right before we went on break. And that would have been cumulus, mature, dissipating. Cumulus, mature, dissipating. So those are your questions for chapter 6 quiz, and we'll try to put some more grades in the grade book for you for a quiz for chapter 6. So at this point, I'll keep moving forward. We're just about to finish chapter 6, and there's literally only a few slides left. Looks like 2 slides. And our slide says restrictions to visibility. So particles that absorb, scatter, or reflect light can limit visibility. Quality of the air plays an important role in visibility. So you guys have heard about smog, you know, like in San Francisco and Seattle, a lot of these bigger cities, the visibility sucks because there's so much pollution, air quality. With this whole coronavirus, you're hearing a lot about China, and there are these large cities in China. They have these like before and after pictures, or even in America, I think Los Angeles, there's these before and after pictures where it's just incredible the difference of air quality without so many people driving around, pollution. Looks like somebody got kicked out. I'm going to let him back in. Oh, Jake. He got kicked out, but we're letting him back in. Cool. So restrictions of visibility. It could be a hazard for us as a pilot. We physically need to see to be able to land or take off. If you're a VFR pilot, you need to be able to see to be able to fly from point A to point B. So if it's a really hazy day, it's more difficult to see. I'll tell you what's really tricky, flying into the sun on a hazy day. if you're flying into the sun on a hazy day, it's dang near IFR. Even if it is visual conditions, it's very difficult to see when there's a whole lot of moisture in the atmosphere. They call it mist, M-I-S-T, mist. So mist versus drizzle, mist versus drizzle. Mist, this is a vocabulary, mist is a reduction in visibility due to the amount of moisture in the atmosphere. Mist is a reduction of visibility due to the amount of moisture in the atmosphere. Different from drizzle. Drizzle is where we actually have small droplets that are falling from the sky. So mist, by definition, is not truly precipitation, whereas drizzle is precipitation. So if it's a mist day, you might have some reductions of visibility, and it's because all those particles in the atmosphere, all those water droplets, all the pollution. Restrictions to visibility. Okay, volcanic ash. Volcanic ash is not something we experience a lot here in Flatland, Indiana, but it would be tiny abrasive rocks that clog and destroy moving parts and intakes. If volcanic ash is encountered, do not enter. If encountered inadvertently, turn around. So it's very bad, very, 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 very bad for your engine. So your engine is like it's like your lungs. Your engine has to breathe in air to be able to create power. You know, if you're like running a mile and you start breathing in, you know, a bunch of smoke and volcanic ash, your lungs are not going to be able to do a good job to provide you energy to keep running. So if you fly your airplane into volcanic ash, smoke cloud, your engine's not going to want to perform very well either. It can straight up damage, destroy your engine. So volcanic ash is bad, bad stuff. Do not fly your airplane into volcanic ash. There have been many times that I've been flying and I've encountered very large smoke clouds. You hear about, you know, and there's, I think I did a trip to Alaska and back a few years ago, and there was widespread fires all over Canada. And we literally had to divert off course miles out of our way because we didn't want to fly our airplane through the large smoke clouds. So smoke is not as bad as volcanic ash, but it's the same principle. You want to avoid putting contaminants into your engine if you can help it. So volcanic ash, do not enter volcanic ash cloud. A smoke cloud is not as bad, but you still want to avoid it if you can. These are weather hazards. And that takes us to the end. We are officially through with chapter 6, which is weather theory. Oh, okay, weather theory. So that was chapter 6. Anybody have any questions, thoughts about weather theory, chapter 6? So, you know, I had somebody talking to me about the weather. You know, you guys have all had somebody talk to you about the weather before. And somebody said, what do you do if you're having flooding problems in your house?
I have no idea.
Well, I know a guy, N-O-A-H, like Noah in the Ark. Well, I know a guy.
Oh my god.
Oh, jeez.
There's not a lot of good weather jokes out there.
I came across one the other day. It was called, it's what's a cloud's favorite drink? Mountain Dew.
Love it, love it.
Here, what's a weatherman's favorite reptile? A blizzard.
Oh, jeez.
What did they call Winter after he went to the gym? Jack Frost.
What's it called when it's raining cat or chickens and ducks? Foul weather.
Yeah.
Oh no.
Yeah, that one's. Where does a cloud go to pee?
Oh, no.
Anywhere it wants.
Love it. Love it. Participation is strong today. Well, so that's weather theory. Excellent stuff. And so we are now moving into the next topic, which is weather products. But I hit a wrong button. It's not working. Let's try again.
Oh, I'd like to point out, I think you did leave the record on during the break. So I think there's going to be about a 10 to 12 minute worth of silence on YouTube.
I do it every time. So the idea is that it's confusing because I don't want to be the one that screws up technology. So like for me to like click it on and click it off, like it creates two separate files. And then that creates like, you know, twice as much work when you have, because I have to download, then I have to convert, then I have to re-upload. I mean, for me to just get this one class up, you know, it's like I'm going to be, you know, screwing with video files, you know, until, you know, 3 or 4 o'clock this afternoon. So that way you guys can rewatch it in case you ever want to. But that's what I've been advised by the department, by my boss to do. You know, we didn't sign up to be digital, you know, distance education people. So I got to do everything I can to help you out. So it's just, I'm learning a lot about video editing and production and all this as well. So it's just way more simple on my end if I leave it as one file instead of having to screw with multiple files as well. But yeah, so if you go back and watch them on YouTube, you'll actually get the 10-minute break as well, but you can fast forward if you want to.
I got you. I've never noticed it on my laptop. I'm just on my phone now, and I just saw the record button at the top still. But yep. I got you now.
Yep. Cool. Yep. Weather theory, but now, weather products. So weather products, I believe you guys are seeing interpreting weather data, the forecasting process. Oh, yeah, okay. So weather data. So we want to create forecasts. We got to analyze data surrounding weather. Okay. So there's lots of different ways to go about this. It starts first with observations. We have to make observations about the weather. What's the temperature, pressure, moisture? And then we're going to make some processing, supercomputers and forecasters, intelligent, trained human beings. And then they're going to create weather products and disseminate those weather products to the rest of the world. So we all can have an idea what's going on out the window. So there's a few different ways to create weather forecasts, a few different products we can create, a few different ways. The forecasting methods. It's kind of a history lesson. We have what's called a basic short-term forecast, and that would be for just a few hours, the few hours ahead. First one would be called a persistence forecast. And the example is that, hey, if it's sunny, clear, blue skies this morning, it should be a great day for a picnic this afternoon. So persistence. Right now it's clear and beautiful outside. I can see out the window here in the front room. It looks like a blue sky, looks great. I just assume that everything's going to persist the exact same as what I see it right this moment. And I assume, you know, here in a few hours, it's the exact same. Persistence forecast. Trend forecast. So trend, now you're starting to try to look into the future a bit, analyzing other variables than what's happening right here, right now. So trend forecast, maybe the example could be there's a cold front moving about 30 miles an hour. That's a pretty fast moving weather system. Cold front moving about 30 miles per hour, and it's about 60 miles away. It should be here in about 2 hours. That would be a trend forecast. Again, it's just another way to develop a short-term forecast. Again, this is kind of more of a history lesson about all the different ways we could predict weather. Analog forecast, that's where you learn from history, comparing current charts to historical charts to predict what will occur. So maybe, years ago, there was a weather system with a low pressure system and it had a cold front in this exact same spot. So here we are years later trying to predict what's going to happen because based on history. But unfortunately, there's just far too many variables for this to be accurate. It could be useful for predicting such things as minimum or maximum temperatures, but too many variables. And this is kind of the idea of like the farmer's almanac. If you can buy a farmer's almanac, it comes out once a year. It could try to predict, when the hottest time of the summer is going to be, when the correct time for the farmer to plant, when the correct time for the farmer to harvest might be, things of that nature. Ooh, advanced methods. Now we're talking meteorological forecast. So that would be the human method. There's going to be a forecaster who uses scientific knowledge of the atmospheric process to predict the weather. So that's what the weatherman's doing. Every station has their own weatherman, and they're trying to predict what's going to happen. Meteorological forecast. Numerical weather prediction. We call this the machine method, numerical weather prediction, where there's powerful supercomputers that determine and predict millions of variables over a 5 to 10 minute span, repeat the process over and over until a forecast for the next day or two is developed. So those are some advanced methods of weather forecasting. Those are forecasting methods. Takes us into observations. So these are all different types of observation stations. So what we're looking at right now is all the different types of observation stations. Let's see. Observation stations, we can see that there are observation stations at airports. This is what we see at like Indianapolis International Airport, even at Eagle Creek Airport. They don't even have to be at airports. They're all around the city. It's just a small weather station that is able to sense wind, temperature, pressure. There's even a small eye where it looks up into the sky and tells us what height the cloud bases are located. The cloud bases are reported as AGL. That's noteworthy. Write that in your notes. Cloud-based information from a AWOS station is AGL, above ground level. In addition to these weather stations scattered throughout our city and airports, we have some weather stations that are scattered throughout the ocean shoreline area. They're out there on buoys, and they're doing a lot of the exact same information, gathering weather data for us to use and disseminate. We also have here a weather balloon. Weather balloons are super interesting. They launch them, I want to say, twice a day. And this weather balloon launches up into the atmosphere, and it's one of the only ways that we can get information about the upper atmosphere. We have lots and lots and lots of surface observation stations. We don't have very many. The only way we can really get upper atmosphere information is from a weather balloon or an aircraft. And then here is a satellite. So nowadays we can use satellites to help us predict the weather as well. And there's lots of different satellite-based weather products we'll get to talk about in this chapter. So that's probably going to conclude us here, because I see that we're at 12:30. So my goal is not to have us go over. So if anybody has any, open general comments, questions, now's the time. I really appreciate you guys putting in the time this afternoon.
So that question someone had a while back regarding the base of the cloud layer, I actually posted that on Slack, the one that he was confused about. I think that's the right one.
Okay, I can look at it right now if you guys want me to. So I'm on Slack and Dylan found one. Let me see if I can bring it up over here. Oh, snap. Gosh, what did I just do? VU flight, here's Dylan. Okay, so it sounds like I'm gonna walk through this question. If somebody has to go, feel free, thank you. But if anybody wants to stick around and hear the answer to this question, I'm right here to work you through it. And
No, you see that's adding the field. It's saying to add the field elevation. So that's probably what I messed up on, because I don't know if I just skimmed through it too fast but I definitely didn't see the field elevation part of the question.
Yeah, that's what I did the first time too.
Yep.
there it is. So what's the approximate base of the cumulus clouds? So you got to be careful because it's saying cumulus clouds. I don't know. Are you guys seeing it? I don't think you are. Let me try again. There you go. What is the approximate base of the cumulus clouds if the surface air temperature at 1000 MSL is 70 Fahrenheit and the dew point is 48? So I'm just opening up my phone and I have a calculator right there. And so I have 70 degrees, subtract 48. So the temperature dew point spread is 22 degrees Fahrenheit. I'm going to divide by 4.4, and that gives me an answer of 5. So I'm expecting the base of the clouds to be 5,000 AGL above the ground. However, the answers are MSL, and it says that the 1,000 foot temperature MSL was 70. So I need to add that 1,000 to my 5 answer. So that's going to put me at what, 6,000 for the correct answer? Yeah, great job. Thank you, Dylan, for posting that.
Yeah, no problem.
So this Slack is a great resource for us all. You guys can take pictures and post questions on Slack, and we can all help each other out there. So thank you for the participation there. You know, if there's any other general questions, now's the time before we sign off.
Yes, sir. I was wondering if you could by any chance go over again with the Coriolis force and the frictional force.
Sure, sure. So very simple. Okay, so you're going to have questions on the written that talk about Coriolis force versus friction force. So what you're learning is that upper atmosphere, if you are trying to analyze winds in the upper atmosphere, call that winds aloft. Winds aloft, the air will follow the isobars. Winds aloft, the air will follow the isobars. I think the written question says the word parallel too. So winds aloft, the upper atmosphere winds, they will follow parallel with the isobars. Why? Because of Coriolis force. That's the upper winds. So if you can write down that statement, if you can memorize that statement, you'll get through the written exam. The winds aloft flow with, they follow parallel to the isobars. Why? Because of Coriolis force. Versus new bullet point, new subject, versus the surface winds. The surface winds will actually cross the isobars at an angle. The surface winds cross the isobars at an angle. Why? Friction force, skin friction, frictional force of planet Earth. I could open up a weather chart and share it, but you know, I don't want to get involved in a 5 or 10 minute thing. The simple answer is that all energy wants to go from high pressure to low pressure. So on that surface analysis chart, you imagine the high pressure center, the wind wants to go straight to the low pressure center, but the Earth is spinning beneath. And the air is not attached to the surface of the Earth. So as the high pressure tries to move towards the low pressure, the route of the air is deflected to the right because of Coriolis force.
Copy.
So I don't know if that's helpful or if that answers the question or if I need to elaborate more or if that's what you're hung up on.
Yes, sir. That answers it. Thank you.
Yeah, great questions, you know, so if there's any questions, I'm more than happy to spend some time answering them.
I had a question about when we're supposed to sign up for next semester.
Okay. So I am an academic advisor. I have not been an academic advisor forever, so I'm not the best at it, but I'm learning. I have emails about this from the boss, and I think the boss email said something about hold off on the advising process right now. So typically, like right now, I would be registering students for upcoming semesters. Like if you were trying to take a summer course or if you were trying to take a fall course, I would typically be trying to register you for that. I might be your advisor. Sean McDermott might be your advisor. Jason Napier might be your advisor. So if you're a flight student, which you are in this class, then one of us three is your advisor: Jason, Scott, Jason, Sean, or myself. I'm interacting with you, so I don't mind doing that for you. Whether or not I'm your real advisor, I don't know, but I can probably help you. I will double check the email, but I'm pretty sure that I've been instructed to hold off and not register anybody in new classes for the moment being. I think that as far as summer goes, I don't think there's going to be any summer courses offered from our department because they want all of us flight instructors out there flying to try to make up for the students that are getting behind here in this spring semester. But I'm thinking that we will register you for fall classes if that's what you're looking for, but I think that I'm supposed to hold off on that for now, but I will get back to you if that changes. I'll make a note.
Could we review that the first part of next session on Wednesday so we could, get a good overall understanding of what you've learned from today about that?
Are you talking about advising?
Yeah, for like next semester and all, fall courses and all that. Like, if you find out anything else regarding it.
Sure. Yeah. I mean, I understand, and that's not a problem. I understand we're past 12:30, so some people may have already logged off. I will revisit and communicate more about advising to you next time. I'm thinking that we're holding off for fall registering, but it'll happen sooner than later. So I will definitely keep you posted. Thank you for that.
I was just trying to make sure we got that taken care of for next class for everyone else. Just trying to be the reminder.
Thank you, Nick.
I think that's all, and I'm going to head out.
Hey, have a great day, Nick. Thank you.
You too.
So I appreciate you guys putting in the time. I'm hanging out here to make sure everybody's questions are answered, but if you got to go, have yourself a great day. Enjoy the sunshine.
All right. You have a good one.
Have
a good one.
Thank you, sir. Have a good one.
Hey, thank you.